Okay, Bismillahirrahmanirrahim. So today our topic is called the reaction kinetics. So whenever you see the word kinetics, the first thing that you should think about is the speed, the rate of reaction. And this is an extension of topic 8 from your AS. In the older syllabus, this topic will be called topic 8. So whenever you see a topic 8, that means it's just the extension from the AS. Okay, so when we look at rate of reaction, it is a measure of how fast the concentration of reactants decreasing or how fast the concentration of products increasing. Okay, so in short, the rate of reaction is equals to change in concentration over time, the time taken for the concentration to increase or decrease depending on if you're looking at the concentration of reactants or the concentration of products. So by looking at the expression for rate of reaction, you can see that it's concentration over time. So you would expect the units to be mole per dm cube per second. Okay, so the mole per dm cube is for the concentration, and the time, usually it's in seconds, but you follow the question. If the question wants the time to be in minutes or hour, then there are also other accepted units. Okay. Next. The concentration time graph is also something that I think you have seen before. So if you are looking at the concentration time graph of a reactant, obviously at the start of the reaction, you would have 0 reactants, and over time, you start producing more and more until you come to what we call a plateau. That means a flat line. It just means that the concentration of the reactants is no longer increasing. That means that's the maximum amount of reactants you can produce. Okay, and at this point, okay, when your concentration time graph reaches a plateau or a flat line, that's when your reaction is complete. Okay, if this was a the concentration time graph of a product, of course, you will start from a certain amount and then it will decrease again for the same, sorry. This is not reactants, I'm sorry. This is products, okay? Initially, you do not have any products, and then over time, you produce more and more products. So if it's reactants, it's the opposite. You start with a certain amount of reactants, and then as your reactants is being used up, it decreases until you reach a plateau. Okay, so if you want to find the rate of reaction graphically, okay, you can use the concentration time graph, right? Because by definition, rate of reaction is change in concentration, which is your y-axis, over the change in time, which is your x-axis. So if you take the change of y values over the change of x values in your graph, I hope you can see that this is your gradient. Okay, now the only problem is your concentration is a curve. Okay, whether it's increasing or decreasing, it's still going to be a curve. And if you have a curve, that means that the gradient at each point of your curve will be different, correct? It's not a constant gradient if you look at it mathematically. Okay, so when you want to find the rate of a reaction at a certain time or at a certain concentration, you have to draw a tangent to that particular time or concentration. Usually we don't really talk about the time. The one that we're interested in is concentration. Okay, what is the rate at, for example, I'm just going to make up my number. This is my concentration 0, and then maybe this is my concentration at 1, and then this is concentration at 1.5 mole per dm cube. Okay, so if the question asks you what is the initial rate of reaction given the concentration time graph, then you would draw a tangent that passes through 0. Okay, that's when your concentration of your product is 0. And then when the question is asking you what is the rate of reaction when the concentration of the product is 1, then you draw a tangent line that passes through where the concentration of the product is 1, and so on. Okay, so if you notice the steepness of my line, okay, the steepness is like how the angle, okay, so you can see the angle of my tangent. If the angle is big, okay, like if you see that angle to the horizontal line, that means the gradient is steep. Okay, so as you can see, the angle is decreasing. Okay, I hope you know what angle I'm talking about here. Okay, so if the gradient is steep, that means the rate is high. So if you are going to calculate this using y2 minus y1 over x2 minus x1, you would see that this number would be the biggest. And if you compare to the line here, where the angle is smaller, okay, we call this gentle. Okay, so it's steep versus gentle. And the gradient would also be smaller, which indicates the rate is getting smaller or slower. Okay, so over time, actually, as the concentration of your products increasing or the concentration of your reactants decreasing, your rate is also decreasing, because at the start of your reaction, you have a lot of reactants. Okay, a lot of collisions can happen. So that's where your your rate of reaction is the fastest. And then as more and more reactants is being used up, you now have less or fewer collisions, therefore your rate is also decreasing. So that explains the decreasing in slope of your gradient. Okay, so the gradient decreases as the reaction proceeds, showing the rate is slowing down until eventually you get to a flat line. And if you draw a gradient through the flat line, it's a horizontal line and the gradient is 0. That means rate is 0, no reaction is happening. The reaction has complete. So initially, the rate is fastest because of the higher frequency of collisions between reactants. Over time, the rate of reaction slows down because there are fewer reactants to collide. So that is the explanation as to why your rate of reaction decreases. Okay, and this is something that I'm sure you have observed in experiments where initially at the start of a reaction, the reaction is very vigorous. The bubble produced is in a big amount, and then as time passes by, the bubble starts to slow down. Okay, so the reason for that is because of this reason here. All right, so you should include that in your notes already. Okay, so this is what I was saying just now. The steeper the gradient of the graph, the faster the reaction is. When the graph is horizontal, gradient is 0. That means your rate is also 0. No reaction is happening. This is the graph of a concentration time graph for a reactance. Okay, so forgive me, I made a mistake earlier just now. This is the graph of a concentration time graph of a product. Just remember, at the start, your concentration is 0. That means you do not have any product at the beginning. Whereas this is how it looks like for a concentration time graph of a reactant. Same thing, you start at a certain number here. I'm just going to assume that is 1.85, okay? So you start with a certain amount at the start of the reaction. That means your reactants, okay? You must have reactants. If you don't have reactants, then your reaction cannot happen. So same thing, if you want to find the rate of the reaction from a concentration time graph of a reactant, you will draw a gradient. Okay, again, if you want to find the initial rate of reaction, you must draw a tangent at T equals to 0, or where your concentration is equals to 0. Sorry, your concentration is not equal to 0. Your concentration is your initial concentration. That means at the start. Okay. And then again, you can see that my line, my tangent, is also getting gentler. Okay. So the angle is decreasing. So that means my gradient is also decreasing. My rate is slowing down. So that's the most important thing that you need to understand, that as my concentration of reactants decreases, my rate decreases as well. As my concentration of products increases, my rate decreases as well. So it depends on who you are looking for, whether you are looking at the point of view of a reactant or the point of view of a product. Okay, so if we know that over time the concentration, over time the rate decreases, okay, so we can also plot the rate concentration graph. Okay, so this is the rate concentration graph of I believe this is of a reactant. Okay, so you probably don't have this, but don't worry. You will see a lot more graphs for a rate concentration graph. Okay, so concentration time graph is, I believe, common already for you to see, but rate concentration graph is not as common, right? But I will just go through this quickly. So you can see here, at your highest concentration of your reactant, that is also your highest rate. And as your concentrations decreases, your rate is also slowing down. This relationship is what we call directly proportional, right? So what it means by directly proportional is that if I increase my concentration by, sorry, if I increase my concentration by 2, that means my rate also increased by 2. Okay. If I increase my concentration by 3, my rate also increased by 3. Okay, but don't worry about that for now. Next, okay, after pretty much some of it you already know, okay, this is totally new for you. The next part is called the rate equation. So the first learning objective is to explain and use some of the terms. Rate equation, order of reaction, overall order of reaction, and rate constant. Rate constant, half-life. Okay, rate determining step and intermediate will be dealt with later on. Okay, and then understand and use the rate equations of the form rate equals to K times concentration to the power of M times concentration of B to the power of N. Okay, so this is how your rate equation looks like. rate is equals to K, where K is your rate constant. Okay, so rate constant is just like your equilibrium constant. It is constant at the same temperature, but this one we have an additional requirement. The activation energy must also be the same. Okay, if you change the activation energy of the reaction, then your rate constant changes. The units depend on the equation, the same way you work out for the units of equilibrium constant. Okay, so we will do a little bit of practice later on. Okay, rate, as you know, has a unit of mole per dm cube per second. Okay, A is the concentration of your species. Either this is a reactant or this is a product. Okay, unlike your equilibrium constant, where you have concentration of products over concentration of reactants, your rate equation, the species, cannot be predicted from the equation. Okay, you cannot use the equation and say, oh, okay, it's products over reactants, or it's reactants times reactants. This information, okay, the information that you put in the rate equation depends on experimental data. Okay, so I will talk about that later on. But just know that the square bracket represents concentration, and each square bracket has a unit of mole per dm cube. Okay, M is the power that you raise the concentration of your reagent A. Okay, M is called the order of reaction. So order of reaction is usually respective to a particular species. So if A is raised to the power of M, that means, okay, I say that M is the order with respect to A. Okay, N is the power for B. So M and N are your integers. It can be 0, 1, 2, and 3. Okay, where 0 means zero order, 1 means first order, 2 means second order, 3 means third order, but you will not see third order for the individual order of reaction. Okay, so for example, if M is 1, I say that the reaction is first order with respect to A. Okay, if N is 0, then I say the reaction is zero order with respect to B. So the order is individual number with respect to that particular reagent. Okay, so that's individual order of reaction. There's also what we call a total order of reaction, or sometimes they will use the word overall order of reaction. It is when you add the numbers M and N together. So if M is 1 just now, N is 0, the overall order of the reaction is 1. Okay. Okay, so the powers, they don't have units. Order, they don't have units. Okay, they're just integers, they're just numbers. Just like how you would raise your concentration for the equilibrium constant to the power of their mole ratio. Okay, it's the same thing. But the tricky bit about the rate equation is that you cannot find this information from a balanced equation. Okay, the orders have nothing to do with the stoichiometry number. The mole ratio will not help you to write down the rate equation. Okay, you have to work it out experimentally. Your rate equation may not include all or any of the reactants. So this is what I said. A and B can be all reactants or no reactants at all, just products or a combination of reactants and products. How do we know that? We don't until we get the results from the experiment. Okay. Right, so here's some example of a rate equation and also the reaction that accompanies it. Okay, so the first reaction we're going to look at the reaction of hydrogen with nitrogen monoxide to form 2 moles of H2O water and 1 mole of nitrogen. The rate equation for this reaction is rate equals to K. Your K must always be there because it is a rate constant. Concentration of hydrogen. So that's your concentration of reactant. But you see here, the hydrogen, the mole ratio is 2, correct? But the order, the power here is only 1. So there's no relation. No relation of order with the mole ratio. But here we say that the order of the reaction is first order with respect to hydrogen. Okay, and then times by the concentration of nitrogen monoxide, which is the other reactant, and the order is 2. Okay, so again, here we say that the reaction is second order with respect to NO, or we say the order of nitrogen monoxide is 2 or second order. Overall, oh, maybe smaller. Overall order of reaction is 3. So you just add up the individual order of reaction. Okay. Next example is reaction of nitrogen monoxide, carbon monoxide, and oxygen to form nitrogen dioxide and carbon dioxide. The rate equation for this reaction is K, which is the rate constant, times by the concentration of nitrogen monoxide to the power of 2. That means the reaction is second order with respect to nitrogen monoxide. Notice that carbon monoxide and oxygen is not included in the rates of in the rate equation. Okay, and that is possible too. Why? How do we know that? Well, we don't have enough information to help us deduce. Okay, so just write down the overall order is 2 for this reaction. Okay, and lastly, nitrogen atom, 2 moles of nitrogen atom to form nitrogen gas, nitrogen molecule. And the rate equation is K times the power of nitrogen atom, K times the concentration of nitrogen atom raised to the power of 2 times by the concentration of nitrogen raised to the power of 1. So you notice that this is a product. And yes, product can also be included in your rate equation. So your overall order of reaction or total order of reaction is 3. Okay, so don't confuse your overall order of reaction and your individual order of reaction. Okay. So what I want you to get out of this is there is no relationship between the rate equation and the chemical equation. Okay, actually the rate of reaction depends on the mechanisms, which you will look at later in the second part of this topic. Okay, moving on. Explain and use the terms rate constant. Okay, so the rate constant K, units of K depends on the overall order of the reaction. It must be worked out from the rate equation. Value of K is independent of concentration and time. So that means if you change the concentration or you change the time, your K stays constant. Okay, so K is constant at a fixed temperature. And just now earlier on, I mentioned at a fixed activation energy as well. Okay, so there's nothing new with constant K. So I would just like to quickly work out the units of constant K. So we're looking at the overall order of reaction. Okay, so I'm just going to use ABCs, okay, as my reagent. So if I have a rate equals to K times concentration of A to the power of 1, that means overall first order. Okay, to work out my units of K, I must remember that the units of rate of reaction is change in concentration, mole per dm cube, over time. And the unit for concentration is mole per dm cube. So if I want to work out the units of K, it's mole per dm cube per second over mole per dm cube. Okay, so when you have a reaction that has an overall order of first order, the unit is S to the power of -1. I suggest you to not memorize this because you can work it out easily. Okay, don't try to memorize the units of K for an overall first order. Okay, so another example, overall second order. For example, I have rate is equals to K times A times B. Okay, again, same thing. I've got my rate as mole per dm cube per second, and A and B would be mole per dm cube times mole per dm cube. So to find the units of K, it will be mole per dm cube per second over the square of mole per dm cube, because I've got two brackets multiplying with each other. Okay. So just cancel out and you should be left with mole -1 dm cube s -1. Don't forget you're bringing this term up. So that's why the sign changes. Can follow so far? Okay. Third example is when you have an overall third order. For example, rate is equals to K times A to the power of 2, B to the power of 1. Okay, same thing. I'll just jump straight. K is equals to mole per dm cube per second over mole per dm cube square times mole per dm cube. So the overall is 3 here. Cancel out and I bring this expression up. So K should be mole -2 dm6 s -1. Okay, so it is worth practicing it now so that you know what to do in the exam later on. Okay. If you're done with that, we will move on. So Danish is here, so that means Ridwan and Hazur are absent. Okay. Right, next we're going to look at the order of reaction. How do we find the order of reaction, or what this order of reaction means? So far, we've only know them as the power, okay, the power of the concentration. The learning objective is to deduce the order of a reaction from concentration time graphs or from experimental data relating to the initial rates method and half-life method. Interpret experimental data. Okay, that's a lot of things. Okay, so order of reaction is usually with respect to a particular reactant or a particular product, okay? Basically to a particular species, all right? It is the power to which the concentration of the reactant is raised in the rate equation. Okay, we know that already. The order of reaction can be 0, first, second, or third. But I think for your syllabus, we only look at individual order of reaction up until the second order, okay? Overall order of reaction is the sum of the powers of the reactants in a rate equation. Okay, that's also something that you are familiar with already, okay? Right, so what does it mean if a reagent or if a species is 0 order? Okay, for 0 order, that means the concentration of A has no effect on the rate of reaction. Okay, so what it means that if we increase, say we double the concentration of A, the rate of reaction stays unchanged. Okay, which doesn't make sense because I think all this while we learned that whenever you increase the concentration of a species, you increase the concentration of your reactants, the rate, the speed increases as well. Okay, so that is only partially true, because if a reagent is what we call 0 order, increasing the concentration will not have any effect on the rate. And if we were to look at the graph, okay, rate over concentration. So if you look at the concentration of A, for example, our species, at 0.1, the rate is 0.00110 mole per dm cube per second. If I double it, 0.2, the rate is still the same. If I triple it, or if I increase by 10 folds, the rate stays the same. Okay, it doesn't speed up. So this is an example of a 0 order. That means our species A is 0 order with respect to A. Okay, so how do we write them? How do we write that down? Okay, so rate is equals to K, your rate constant, times concentration of A to the power of 0. Now, what is anything to the power of 0? It's just 1, right? Anything to the power of 0 is just 1. So you will not see the concentration of A in your expression. Okay, another way of writing this down is rate is just equals to K. So this explains why sometimes your reactants don't appear in the rate equation. They are probably because it has a 0 order. Okay, so graphically, you need to recognize how a graph of a rate concentration time graph looks like for a 0 order. Okay, first order, the rate is directly proportional to concentration of A. So that means if you increase, if you increase your concentration, your rate also increase by the same amount. Okay, so that's what we mean by directly proportional. I will show you later on how to do the calculation or to show numerically what it means by directly proportional. Okay, when something is directly proportional, you would expect the graph to be a straight line that passes through 0. Okay, so remember, for a first order, individual first order, the graph of the rate concentration would be a straight line passing through the origin. Okay. So it means that if we double the concentration of A, the rate of reaction also doubles. And if you write that down in the equation, it appears like that, A to the power of 1. It means that the reaction is first order with respect to A. Second order, the rate is proportional to the square of concentration of A. What does it mean by this? So if we double the concentration of A, that means, for example, double is times 2, the rate increases by a factor of 4. Oops, sorry. Factor of 4. So it's the square of your concentration. That means if you, okay, so that's times 2. If you increase the concentration by 3, your rate would increase by 9. Okay, it must be the square of your concentration. So how does a second order looks like graphically? When you plot the graph of rate against concentration, it would increase, but this time it doesn't increase in a straight line. It increases in a curve. Okay, so when you double the concentration, or when you increase the concentration, the rate will increase by the square of your concentration. Okay, again, I'll show you later on with using numbers. Okay, right. So overall, in summary, okay, zero order means the concentration has no effect on the rate of the reaction. That means increasing or decreasing concentration, your rate of reaction stays constant. First order, directly proportional. You increase your concentration by 2, your rate increases by 2. You increase your concentration by 5, your rate increases by 5. That's what it means for directly proportional. For second order, proportional to the square of concentration. For example, if I increase my concentration by 2, my rate will increase by 4. If I increase my concentration by 5, my rate will increase by 25, because that's the square. Okay, so be careful with the square. So I'll just show you. Increase by 2, rate will go up by 4, concentration rate. If you increase concentration by 5, the rate will increase by 25. Okay, so it's not increasing by 10. It will have to be the square. Okay, right. So finding orders of reaction graphically. Okay, interpret experimental data in graphical form, including concentration time graph and rate concentration graph. So please be careful that there are 2 types of graphs here. One, the concentration time graph, and the other one is rate concentration. So far, we've looked at the rate concentration time graph of a 0, first and second order of a reaction. Okay, there are 3 ways to identify the order from graphs. I mean, 3 ways to identify the order. First, from the rate concentration graph, which we have looked at just now. The next one that we're going to look at is concentration time graph. And lastly is half-lives. Okay, so half-lives can be Hello, sorry. Hold on. Hello, sorry about that. Okay, so um, how can we use the rate concentration graph to find the order? Okay, so basically we can use the initial rates. Okay, so when you use different concentration, of course, the rate will change over time. Okay, so we just focus on using initial rates. That means when the time is equals to 0. Okay, that means it's the same lah as initial concentration. These rates can then be plotted against time in a rate time graph. Okay, so here is your 0 order. We're still looking at the rate concentration time graph because I just want to use numbers this time. So the reaction is 0 order with respect to A. If you're wondering what A is just any species, okay, whether it's a reactant or whether it's a product. The concentration of A does not affect the rate of reaction. A horizontal straight line on the rate concentration graph shows a 0 order. So if you see a horizontal line, then it should automatically click. You should already think about, that means it's a 0 order, okay? First order, okay, so this is what I want to show you, where it says that the graph shows the rate is proportional to the concentration of A. So what do I mean by that? And how do we use our graph? Okay, so I'm going to first take 0.1 and 0.2. Okay, so that means concentration increase from 0.1 to 0.2. Okay, so that means if you put this in a calculator, well, you can already see that that is an increase by 2. Okay, take the bigger number, 0.2, divide by 0.1. That means that's an increase in a factor of 2 times 2. Okay, and then you read the rate. Okay, you read the rate at 0.10. I have, it's not easy to read the graph because it's actually not a graph, okay? But I'm just going to use an easy value, which is 0.0075, and it increases to, if you read here, 0.025. 0.0125. Okay, so this is the effect of increasing my concentration by a factor of 2 times 2, and my rate is 0.0125 divided by 0.0075. Okay, and that is an increase by 1.6. So because this is an experiment, and also because my graph is not, I mean, I'm not reading it accurately, but can you see that 1.6, it's near and close to 2, right? So that means if I increase my concentration by 2, my rate also goes up by 2. Okay, so estimate like approximately 2. Okay. Another example. Okay, so that's the first one. You can also choose, for example, if my concentration, next I want to take 0.2 to 0.4. Okay, just to show you how it's done. So again, my concentration goes from 0.2 to 0.4. And this is an increase in 2 as well, 0.4 divided by 0.2. So that's an increase by 2 times 2. So my rate, I go from 0.0125 to 0.0225. Okay, same thing. How do I find how much the increase is? I take the bigger number, divide by the smaller number. So if you put that in your calculator, 0.0125, then that comes out as 1.8, okay, which is also approximately 2. Okay, so this is an example where whatever amount you increase the concentration in, your rate will also increase by the same amount. That is the criteria of a first order. And that's what we mean by directly proportional. Okay. So whenever you see a rate concentration graph and there is a straight line through the origin, that should be first order. But if you're not given graphs, you're given values instead, then you would use this method. Okay, find how much your concentration is increasing and then find how much your rate is increasing as well. You don't necessarily have to start with times 2. You can also do times 3 or times 4, all right, which you will look at later on. It's not always a nice number, but for this one, because the graph is not that great, so I'm just going to use nice number. Okay. Next, we're going to look at second order. Second order, just now it says that the rate is proportional to the square of your concentration. Okay, so let's see what happens. My concentration, I'm going to take 0.4 to 0.8. I'm just going to choose a nice number. Of course, whenever you get a graph, always choose a nice number. So my rate goes from 0.0125 to 0.0225. Okay, again, it's actually not, actually it's a little bit off, but I'm just going to go with these numbers. Okay, so 0.8 divided by 0.4, you can see that it's an increase by 2. And then so the rate 0.0225 divided by 0.0125 is 0. Wait, that's not right. 0.0125. It should be more actually. 0.0275 divided by 0.0125. It should be times 4 and not times 2. So what's wrong here? 0.0225 divided by 0.0125. That doesn't work. Okay, let me just 0.225. It should be, the rate should be increasing by 4. It's not by 2. So that means this graph is not to scale, I believe. Okay, so please erase this, otherwise you will get confused. Okay. I will show you an example where it works. Okay, so I'm guessing this graph is not drawn to scale because it doesn't match with the second order criteria. Okay, so moving on, our rate concentration time graph, whenever you see a curve, okay, actually, you must not assume that it's a second order because it can be second, third, fourth, fifth, and etc. Okay, because they all will give you a curve. So to confirm a second order, you must find the relationship. Okay, just now, as you can see, that we cannot do it for this graph because this graph is not that great. Another way to confirm is, remember I said that the rate is proportional to the square of the concentration. Okay, so that means, right, if I were to plot a straight line for a reagent that is second order, I must plot the concentration to be squared. Okay, the rate is proportional to the square of the concentration of A. So that means I have to plot concentration of A squared. And if I get a straight line, then can confirm that it is second order. Okay, if it's not a straight line, then that means this is not true. This expression is not true, right? Because you can see that this is a straight line Y, this is your M, and this is your X plus C. Okay, so I'm looking at the straight line equation, Y equals to MX plus C. Okay. So a straight line in the rate against concentration square time graph shows that the rate of reaction is proportional to the concentration of A squared, right? So this is the summary. Make sure that you understand it is the rate over concentration. Don't get confused with the concentration time graph. This is rate over concentration and rate over concentration. Just to summarize what we, I think this graph shows the second order better because you can see that it is increasing steeply, which shows that if you double the concentration, okay, the rate will also increase by 4, but I don't have the numbers here. Okay, so that means this is 0, first and second order. So when we look at the individual order of reaction for your syllabus, we only look at 0, first and second order. Okay. If they were to combine all the graphs in the same axis, this is how it looks like. Okay. Something that you should already be able to identify, where your 0 is a horizontal straight line, your first order is a straight line that passes through 0, and your second order is a curve increasing. Okay, so I guess that is all for today. I don't want to rush through the concentration time graph, but we will look at that in the next lesson, how different shapes, well, mostly different shapes of concentration time graph can be used to determine where the order of the reaction individually. And then later on, we will look at the half-life. Okay, do you have any questions before we go? Hey, man, the summary. I want to leave it at the summary. Everyone okay with that? Okay, then